So welcome again to another session. So in this session, we are going to study about the Fourier transforms. And the reason why we are going to study the Fourier transform is because as we saw in the previous topic of Fourier series, we were able to express periodic functions in terms of linear combinations of sine waves and cosine waves. But in most practical problems, all the waveforms that we are going to deal with are not necessarily periodic. And so examples of such waveforms are pulse signals and noise signals. So to be able to study them, we need to understand how to do their Fourier transformation to be able to know how to study their behavior and dynamics. So this topic is mostly applied in the communications engineering and signal processing. And so let's start by defining what we mean by Fourier integral representation of a non-periodic function f of f, and then we'll define the Fourier transform of a function, and then its Fourier inverse transform. And then thereafter, in another session, we'll do the examples on how to calculate Fourier transforms of functions. So we'll start by our theorem. Theorem. And the first theorem we state is the Fourier integral representation of a function f. So suppose that we have a piecewise smooth finite function f on a finite interval, such that the integral of the function from minus infinity to positive infinity is finite. Then the Fourier integral representation is given by suppose or we can use the variable t. So the integral of the absolute value of the function f of t So when you say this integral is less than infinity, you mean that it's a finite, has a finite value. Then f has the following Fourier integral representation. That f of t is the same as the integral from 0 to infinity of capital A of k multiplied by cosine of k t plus b of k multiplied by sine of kt dk and then this t lies between negative infinity to positive infinity, where for all values of k which are non-negative, these constants a and b, these quantities a and b are given by 1 over pi integral from minus infinity to positive infinity of f of t multiplied by cosine of kt dt, and the quantity b so this integral, given this, if I call this one star, this expression of f of t, I call it star, then the integral star converges to f of t if f is continuous at the values of t, and the average of the left and right hand limit, so which can just be written as f of t plus f of t minus. So this simply means the average of the right hand and the left hand limit of the function f. So that is the Fourier integral representation. But sometimes we use the complex. What is mostly practically used is the complex form of the integral. And so that takes us to the definition of the Fourier transform. So definition. Of Fourier transform pair. So the Fourier transform of a function f of t is defined by that's Fourier transform of f of t, which we represent as capital F of k, is given by the integral from negative infinity to positive infinity of the function f of t multiplied by e raised to power negative I kt dt, where this f of t can also be expressed in terms of f of k to be 1 over 2 pi integral from minus infinity to positive infinity of capital F of k, and then e raised power I k t dk. So let's call this one equation 1 or formula 1. Let's call this other one 2. So 1 is what we call the Fourier transform of the function f of t. So this one is the Fourier transform of f of t, while this 2 is what we call the inverse Fourier transform. This is what we call the inverse Fourier transform of f of k. So these 1 and 2 together are called, so 1 and 2, equations 1 and 2 form what we call a Fourier transform pair. So 1 and 2 is what we call the Fourier transform pair. So this is the inverse Fourier transform of f of k. Now, one key thing that should be clear from the word go is that there is no universal convention concerning the definition of the integrals we have given in 1 and 2. Different authors or different textbooks will give different formats of the Fourier integral pairs. For instance, so this should be understood from the word go, not. There is no universal convention the definition of these integrals. So for instance, this point, for instance, some authors write the factor one over 2 pi in the first integral instead of so this factor here is written in this integral instead of this second integral. So therefore, those two will be of the form f of k, which is the same as the Fourier transform of the function f of t, will now be written as 1 over 2 pi integral from minus infinity to positive infinity of f of t e raised to negative I k t dt, where then we write f of t will now be given by integral from minus infinity to positive infinity of capital F of k e raised power I k t dk. So this now this will be now 3, and then we call this one 4. So if we do that change, this is how we write the Fourier integral Fourier transform pairs. Also, in some cases, others place a factor of 1 over root 2 pi in both of the integrals 1 and 2, giving some symmetry to the equations. So therefore now, if that's the convention that you pick to write them, then you'll have the Fourier transform pairs, will be the Fourier transform of the function f of t, which is the same as f of k, will be 1 over root 2 pi integral from minus infinity to positive infinity of f of t multiplied by e raised to negative I k t dt, and then f of t is the same as 1 over root 2 pi integral from minus infinity to positive infinity capital F of k e raised to minus I k t dk. So we call this one 5, and then call this one 6. So if you use if you want to show the aspect of symmetric relationship of these two integrals, then this is how we can rewrite 1 and 2 to represent the Fourier transform pairs. But then now, to make things clear, we are going to stick to the definition we have given in the first formula 1 and 2 throughout our computations. So note, we will stick to the definition of Fourier transform pair given in questions 1 and 2. So that's what we are going to be using throughout this chapter. So also, you should actually know that the way we write this integrals, we say that integral 1 is the Fourier transform of f of t is given by integral from minus infinity to positive infinity f of t e raised power negative I k t dt, and then the inverse Fourier transform of f. Remember, this is what you are calling the f of k. This now what gives us the f of t is the 1 over 2 pi minus infinity to positive infinity of f of k e raised power I k t dk. So this is what we gave in 1, and then this is what we are giving in 2. Note that we can as well represent this k can actually be changed to be omega, and we have the same 1 can be written as the Fourier transform of f of t as a function. We can write it in terms of a variable omega, and then it will take the form integral from negative infinity to positive infinity of f of t, and then e raised power negative I now omega t, and then dt. And then its inverse of this f of omega, which gives the f of t, now will be written as 1 over 2 pi integral from minus infinity to positive infinity of capital f of omega e raised power I omega t, and then the omega. So you should actually not fix your mind that when they use a different variable to represent the Fourier transform, you see it as a different formula. We can use any other variable to do that representation. So this is the definition that you are going to stick to when you are working out problems on Fourier transforms and Fourier inverse transforms. So the next session now we do some examples to illustrate how to carry out or how to compute problems involving Fourier transforms. Thank you.